Today, we're solving one of the most deceptively complex challenges in system design, a leaderboard that updates in real time for millions of concurrent players. Think Fortnite, Clash of Clans, Call of Duty. These systems handle 500,000 plus score updates per second during peak events. Sub 100 milliliters latency for rank queries, zero downtime during global tournaments. And they do it all while keeping ties fair, data consistent, and players engaged. Let's break down exactly how this works, from first principles to production-grade architecture.
The problem is to design a leaderboard for an online mobile game. Leaderboard is a board showing who is leading in a game in terms of points or score. Here are some good requirement questions to ask. How is the score calculated? What's the DAU? What's the time element with the leaderboard? How do we break ties? Does the leaderboard have to be real-time? In this slide, we present the high-level design of a real-time gaming leaderboard system, the kind you'd find powering competitive games like Fortnite, Call of Duty, or FIFA. The system needs to support real-time score updates and fast reads for leaderboard rankings. Let's start with the API surface. We expose a post API that updates a player's score and position on the leaderboard. A get API allows fetching the top K players, which is critical for the leaderboard display. Another get API fetches the rank of a specific player, which is useful for showing a user's relative performance. Now for the design flow. When a player finishes a game, the client sends a request to the game service. The game service contacts the leaderboard service to update the player's score. The leaderboard service then updates the leaderboard store, ensuring the scores reflect the latest game outcomes. Players can call the leaderboard service directly to retrieve top K rankings or their personal rank. If scores are consumed by multiple downstream services like analytics, fraud detection, or notifications, we insert a message queue between the game service and leaderboard service. This ensures decoupled and scalable processing. Under the hood, the leaderboard store uses Redis sorted sets, ideal for ranking systems. Each player is a member of the set and is associated with a numerical score. Redis implements this using a combination of a hash table and a skip list. The skip list allows O-log-n performance for insertions and lookups. Skip lists are multi-level indexed linked lists that efficiently skip over elements, making them well-suited for dynamic sorted data. Redis operations include ZAD, inserts or updates a player's score. Zinkerby, increments a player's score by a delta. Zrange, zrev range, fetches ranges of top or bottom players. Zrank, zrev rank, gets the rank of a specific player. To support millions of active players and real-time updates, scaling the leaderboard store is critical. Redis, our choice for the leaderboard store due to its low latency and sorted set data structure, must be partitioned effectively to handle both read and write load. We use fixed partitioning, also known as range-based partitioning, to horizontally scale Redis. Specifically, we partition leaderboard data by score range. For instance, one Redis instance might handle scores from 0, 1000, another handles 1001, 5000, and so on. This way, each shard only manages a portion of the overall leaderboard data. This technique allows the ZAD, Zinkerby, and Zrank operations to remain performant even as the number of players scales. Since scores are typically concentrated within certain ranges, we can proactively allocate more capacity or replicas to hot partitions, those with the most activity, to avoid bottlenecks. However, this approach also introduces some challenges. For example, if a player's score increases beyond their current partition's range, we need to migrate their record to another shard. This requires careful orchestration to avoid inconsistencies during score updates. Additionally,
Fetching the top K players globally now requires coordination across multiple partitions. One common solution is to maintain a summary cache or aggregated top scores in a separate fast access structure that's periodically updated from all shards. This setup ensures low latency for updates and queries and forms the backbone of a fast, consistent leaderboard experience for players around the world.